Hello. In this video, we're going to talk about the basics of what we call bivariate data. Again, bivariate data is two variables being measured in a single experiment or observation, right? We said for bivariate data, typically we would think about weather as a good example, because you might want to measure wind speed and temperature, or precipitation level and barometric pressure. Those are kind of two things. Bivariate data are often described by graphs, right? A Cartesian plane with an X and a Y are really good ways to describe how the data works, and some other numerical methods. We're going to talk primarily in this video about graphs, and chapter 10 is really going to focus on the numerical methods. So that's going to be towards the end of the course. The way that we really represent bivariate data is by what we call a scatter plot. And if both of our bivariate data variables are quantitative, we're going to call one of the variables X and the other Y. And we'll consider a single measurement the ordered pair of X comma Y. And what we're going to do is we plot those 2 points, that X and that Y, on a two-dimensional Cartesian plane. And that representation is what we call a scatter plot. So if we just look at a brief example, we might want to know the number of household members and the amount of money they spent on groceries per week. So a 2-person household may have spent $95.75, whereas a 3-person household may have spent $118.33, whereas a 5-person household might have spent upwards of $180 on groceries. If we were to plot those points, we would get something that looks approximately like this: a data point here and here. The interesting thing to do with scatter plots is to try and see, are these data points somehow related? Is there a pattern, right? In this case, we see kind of a straight line drawn. And we're looking at that pattern. Do we see a straight line, or do we see some sort of curved line, right? We're not going to talk really a lot about curved lines in here. These would be like exponential, logarithmic, quadratic, or polynomial, to name a few, right? You can say, maybe the data doesn't go up quite that high, but maybe the data starts to go up, right? And maybe the curve we could fit kind of fits more like this. This is what we would call an exponential curve. Early in the pandemic, we had talked about flattening the curve. The transmission rates of diseases have this exponential curve, and left untreated, a virus will spread very slowly at first. It'll hit some sort of critical mass at some point, and then start to go up really, really steep. And when they talk about flattening the curve, what they're talking about is, instead of it getting to that exponential spot, when you see this growth rate of like days since first infection and number of infected people, they want that thing to somehow flatten out, is to have some sort of point here where the curve flexes down. That's kind of what they're talking about with flattening the curve, because things can grow in a very fast rate. So if we see a pattern, like here, we kind of see a linear pattern, but the question is, how strong is that pattern? What is the strength of that relationship? The strength and direction of this relationship, because, right, if we have a linear relationship, maybe our data points kind of look more like this green. Those data points are going to kind of slope downwards. Let's get rid of these. The direction and strength of that relationship between the X and Y variables are what we call the correlation coefficient R, right? In high school stat, you might have asked to find the R or R squared value of a linear correlation. That's what this is. R tells us the strength and direction. And it will tell us really a lot about the correlation between X and Y. If R is bigger than 0, if it's positive, then what that's going to tell us is R is going to have a positive linear relationship or positive slope, right? That this line, if we know that the line is going to somewhat look like this up and right. If R is negative, then it's going to have a negative linear relationship or a negative slope, right? As we go further along the x-axis, the y-axis values are going to shrink down. Right? A misnomer, a mistake is thinking that, well, the smaller R is, the less likely there is to be a relationship. Not so. R is really going to live between -1 and 1. That's kind of where R lives, between -1 and 1. The closer it is to -1, the stronger negative relationship we have. And the closer R is to +1, the stronger the positive relationship is. And so the question then becomes, well, what if we really don't have a relationship? What value of R gives us kind of no relationship? And the closer R is to 0, if R is approximately 0, then we're not saying R doesn't have a relationship. We're saying R has no linear relationship, right? Exponential growth would not have a very strong linear relationship. Quadratic growth would not have a very strong linear relationship, right? R only tells us the strength and direction of our linear relationship. But even with a very high R value or very small R value, like close to 1 or close to -1 respectively, one thing we want to keep an eye out is that correlation, having a very strong correlation coefficient, does not mean one thing causes another. There's a very famous example of ice cream consumption and violent crime that researchers did and found that as the ice cream consumption increased, violent crime also increased at a very strong positive linear relation rate. That the more a community ate ice cream, the more likely one was to experience some sort of violent crime. And there was a high correlation. However, I don't think anyone could say that ice cream causes monsters, right? That's not what we're trying to say there. I believe what we're trying to say is if R is very strong, if R is very close to 1, a high correlation really means we need to do more investigation to see if there is a causation. Maybe it does cause it. We have to study it, or maybe it doesn't. And when they studied this, they said, well, of course, these two things don't cause each other. There was kind of a third underlying condition, and that was outside temperature. Specifically here, the summer, right? In the summer, you tend to eat more ice cream because it's a nice and enjoyable way to cool down. And it turns out that in the summer, violent crimes are more likely to happen. I mean, think about it now. You're less likely to be outside or to have heated temperatures when it's 20 degrees outside, than when you are when it's 120 degrees outside. Those are two very different aspects to the pathology of violent crime. So we're not really going to talk about how we compute R right now. We're going to save that computation a little bit more for chapter 10. So I just wanted to give a background, kind of the very basics of bivariate data. If you have any questions, again, feel free to contact me. My Zoom and office hours are open to you. If not, have a good day, and I'll talk to you later.